My responsibility was the transmitting subsystem. Here we start with my PCB. It's a 5-volt power supply. This 5-volt power supply powers our signal generator, which is our main component that supplies the 5.8 gigahertz signal to our antennas, which sends the power to the other antenna. Here I have a live demonstration. I'll plug in my signal generator. From this, you can see on the spectrum analyzer that a stable 5.8 gigahertz signal is outputting with also negative 21 dB power. That is about 0.00741 milliwatts. That is why we need this amplifier. The amplifier produces an antenna gain and increases the gain up to 31.6 milliwatts. Using this amplifier, it makes the gain go up to 15 dB, which I said 31.6 milliwatts, which is around 3.56 voltage peak to peak. Looking at that, it was the linear power ratio was 4,266 times using that amplifier. Frequency verification, it passed all tests that we had for frequency. It generates a 5.8 gigahertz, very stable frequency. And then hypothetical free space, if we were going to send power from the antenna to antenna 1 meter away, DC's 1.03 volts. And then it kind of scales down from there. 5 meters, it's 0.2 volts, 10 meters, 0.1 volts, and so on, so on.
After the signal is sent and received by the secondary antenna, it then goes into a voltage rectifier married with a voltage booster. The voltage rectifier essentially acts as an AC to DC converter while also multiplying the voltage by each stage. There are 3 stages, and from what we measured before, our first stage from a 1.25 volt peak input at 15 megahertz, at our first stage we got 1.32 volts, second stage 1.72, and then third stage 1.92 volts. And at the third stage, it then feeds into a storage capacitor that then powers the voltage booster. And 1.92 volts DC is plenty of power to be able to power the booster.
This is where I come in, designing the booster circuit. I designed an Armstrong oscillator circuit. So in standard voltage applications where you want to step up voltage, typically you involve a op amp, which would require an external signal. In this case, this is all closed signal. There's no need for external voltages at all. And here we have it powered, giving 3.5 volts peak to peak, and we're getting an output of 6.72 volts, thus boosting the signal. More testing and more efficiencies can be done to make this boost higher. This does sacrifice amperage in this, so we do lose the amps, but we gain the voltage in this booster, but it can be configured to a lower voltage to actually power a load in a lot of these cases. As Dominic said, we have our values for in our testing, we got these values producing the voltages through the system. We have on our other poster the specific circuit diagrams of our combined receiving subsystem. And that's pretty much it. We worked on this building off of last year's program. It was initially a NASA idea that was given out to many universities, and we pretty much went from there and built what we anticipated to be a more efficient and more separate system. Thank you.